Hamming code error correction and detection study. In the process of communication, the information gets corrupted. Therefore, the signals received by the receiver which is different than the actual information signal. To figure out this problem, the receiver should be able to detect those error bits and correct them. One common way to do this is to add code redundancy. There are two examples. The first one is repetition code. But this method is very expensive where only 33% of codes are original data and 66% of codes are redundancies. Hamming code is a similar and better way of error detection and correction which use redundancy but is much cheaper. In the figure shown here, for 16-bit transmission, 12 bits are original code and 4 bits are redundancies, which means the redundancy only costs 25% of the code. This study stated that how receiver detect the errors in received signals and how does receiver rectify that error by using Hamming code method. In the late 1940s, Richard Hamming recognized that the further development of computers required better consistency. In particular, the capability to detect and correct errors. A huge-scale transmit computer had failed to deliver the expected result due to the failure of hardware. Hamming, one of the dynamic supporters of computer usage, was resolute to find an efficient means by which it could detect and correct their own faults. In the process of transmission, the information gets corrupted. Therefore, we get a signal at the receiver which is different than the original information signal. The general idea for achieving error detection and correction is to add some extra data with the message, which receivers can use to check consistency of the delivered message, and to recover data determined to be corrupted. Here is an example shows how we can apply Hamming code to detect error in the code. Given a 15-bit code, 110110110000110001, and claim that the receiver has received signal which has even parity bits. In this process, we identify the parity bits. It will be the power of 2s. 1, 2, 4, 8 are all the power of 2. So bit 1, bit 2, bit 4, bit 8 are all parity bits. Each parity bit checks different subsets of the code. Parity bit 1 checks 8-bit by checking 1 and skipping 1, which means it will check bit 3, bit 5, bit 7, bit 9, bit 11, bit 13, and bit 15, which are 00100101. There are totally 3 ones, so the parity bit should be 1 to make it even. Parity bit 2 checks 8 bits by checking 2 and skipping 2. So it will check bit 3, bit 6, bit 7, bit 10, bit 11, bit 14, and bit 15, which are 01100101. There are totally 4 ones, so the parity bit should be 0 to make it even. Parity bit 4 checks 8 bits by checking 4 and skipping 4. So it checks bit 5, bit 6, bit 7, bit 12, bit 13, bit 14, and bit 15, which are 0, 0, 1, 0, 1, 0, 1. There are totally 3 ones, so the parity bit should be 0 to make it even. Finally, parity bit 8 checks 8 bits by checking 8 and skipping 8. So it checks bit 9, 10, 11, 12, 13, 14, and 15, which are 0, 0, 1, 1, 0, 0, 1. There are totally 3 ones, so the parity bit should be 1 to make it even. Now we find that the value of parity bit 1 is matched with the value of received signal, and the value of parity bit 2, 4, 8 are not matched with the value of received signal. Therefore, we can make sure that the parity bit 1 is correct and the parity bits 2, bits 4, and bits 8 are incorrect. For finding the incorrect bit, we can add all the incorrect parity bits by adding 2, 4, 8, which is 14. The result 14 means that the value of bit 14 is corrupted. To correct the error bit, a simple flip operation is sufficient, which means 0 will be changed into 1 or 1 will be changed into 0. In this problem, after we find that bit 14 is the error bit, we can just change bit 14 from 0 to 1. Now, let's verify if we have successfully fixed this error. Repeat the previous process. 4 parity bits are 1110. Now we find that the value of all parity bits 1, 2, 4, 8 are matched with the value of received signal. Therefore, the error of the signal has removed. In this way, we can detect and correct the error of received signals. We see from this method how we can detect the error on received sequence of information by checking the value of parity bits. It is found that if the derived values of parity bits are not matched with the value of received signal parity bits, it shows that the signal has some error, and if the values are matched, it means a signal has no error. After detecting the error, we can find that which bit has error by adding the sequence numbers of incorrect parity bits. The result shows the sequence number of incorrect bits. After finding the sequence number of incorrect bits, we can easily correct the error. The biggest drawback of this algorithm is that it can only detect one bit error. When more than one bit of data is corrupted, this algorithm will not work anymore. With the growing amount of data that is communicated, more error will have to be considered. Hence the following questions. Is there any method to detect 2 or even more errors using Hamming code? What is undetected error probability of Hamming code? The case of concatenated code is considered where the inner code decoder reports multi-bit symbol decisions and can save the source information used for the decision. Normally, an alter decoder using a Hamming single error correcting code cannot correct more than one error. But by using what is called soft information single error correction, where a hypothesis that a particular symbol in some alter check set is the only error in the set, can be confirmed or denied by the inner coder. A Hamming single error correcting code of any order can be very easily correct with high confidence any pattern of two errors. In many cases, more than two errors can be corrected, up to a good fraction of even n-k errors of a nk Hamming single error correction code. The ability of a Hamming single error correcting code to correct two or sometimes more vector symbol errors provides a useful tool for interaction of a long Hamming codes interleaved with low density codes at the alter level. The fact that a failure to correct some Hamming subcode often could be fixed by a correction by interleaved code of one of its symbols greatly increased decoding power. A study of interactions would be valuable for future work. Alright, thanks for watching.